I just get 1 over 12 because it's x over 12 is the same with 1 over 12 times x. When I differentiate, x is gone because x prime is 1, and I get this. Now, we also talked about this. Sorry. Okay, one more time. So y equals x over 12 minus 12 over x. So when I differentiate this piece, this is basically this. Don't use the quotient rule on this. So x over 12 is the same with 1 12 times x. So when I differentiate this, I get this. So that is done. We also talked about 1 over x prime. And we said this is negative 1 over x squared. Let's say we don't know this. Just forget about it for a moment. How do I differentiate 12 over x? So I have 12 times x to negative 1. I have to change it. You can use the quotient rule, but it will be too hard. You're making it too hard. So then, when I differentiate this, 12 over x, I bring down negative 1 multiplied by 12 and subtract 1 from the power. Because there is a minus in front, I have to change this into plus. And it's done. This is it. No, I didn't look at any notes yet. Okay, so let's continue. This, what did I just do? So this, we did a problem in class on Monday, more difficult than this. So the graph at which the tangent line is horizontal. So I have y equals, this was the extra credit, negative 0.03 x squared minus 0.9 x plus 50. So all we had to write was y prime equals 0. So negative 0.06 x minus 0.9 equals 0. That's all you had to write. So x equals 0.9 divided by 0.06 with minus in front. That's it. And you use a calculator to divide 0.9 by 0.06. That's 15 with minus in front. So x equals negative 15. And you have to plug it in the y to find the point. That's it. So negative 0.03 x squared. And that's not what I meant. Squared. Okay. And then a minus 0.9 x plus 50. So I just need to plug in negative 15. Yeah, what did I do? Yeah, you didn't like this. Of course, I wouldn't like it either. Good. So negative 15. Okay. So that's the point. Negative 15, comma 56.75. That was it. That's all you had to do. Okay, 18. Okay, I saw somebody differentiated this, differentiated the first function, differentiated the second function, plus differentiate the first function, differentiate the second function. That's not the product rule. We cannot invent the product rule. It was already done. So for g of x equals 5x to negative 3, x to the fourth minus 5x cubed plus 11x minus 9. So if if you just wrote without simplifying, I would have, and I will look again and give you full credit for it. So all you have to do is differentiate the first function as negative 15x to negative 4, copy the second function plus 5x to negative 3, and then differentiate the second function, which is 4x to the third minus 15x squared plus 11. If you just enter it like this, you would have gotten full credit. You don't have to simplify it. I would have given, and again, I'm going to look again and see. Let's see, 19. Do I have to work on 19? You bring down negative 10. You subtract 1 from negative 10, but you have to multiply by 6x. If you didn't multiply by 6x, then you did not use the chain rule, and that is incorrect. Okay, differentiate. This is the product rule again. I only needed to see this, 2x the square root and plus x squared, 1 over 2 the square root of 10x minus 7 times 10. That's it. First function prime times the second plus this first function times the second prime. Yes, this can be further simplified, but I would have given full credit for this, just applying the product rule. Okay, 21. The domain, you have to take the denominator, set it equal to 0, and find the domain. That's just algebra. Here, just take the cube root of 64 to the 4th power. And in any format, I would have given full credit. 23. You have to set them equal to each other and solve a linear equation. It's not quadratic, it's not cubic, it's not radical, nothing, just a linear equation, just algebra. 24. Find the equation of the tangent line to the graph. You have to find the derivative and plug it in. Do you want me to show 24? Anybody?
Can you please? Yes.
Yeah. So we had at least 4 problems like this one. F of x equals 2, negative 2 minus 8x squared, and we have 3 comma negative 74. So we had, if you look at the examples from Monday, so f prime of x is negative 16x. You have to plug in 3, so this is negative 48. So y minus 74 equals negative 48, x minus 3. And we just solve for y. Is this okay? You distribute and then subtract 74. Is this okay? Is this okay, everybody? Okay. And let's see the last one. So we have the cost function, and they want us to find the average cost and then differentiate the average cost. Is this okay? Do we need to work on this problem? We had...
Can we do this one?
Yes, of course. Okay, so we have c of x equals 770 plus 37x minus 0.065x squared. So they want us to find the average cost and then plug in 176. The derivative and plug in 176. So if you go back to the videos and the work from Monday, you're going to see way more complicated examples than this one and last time. Okay, so we have c of x divided by x is 770 times x to negative 1. 37 divided by x is simply 37x divided by x, and minus 0.065x. That's it. And now we differentiate. We bring down -1, x to -2, this prime is 0, and this prime is -0.065. You just have to plug in 176, and that's it. Any questions on this problem? The problems we looked at, they all had rational exponents. They were way more difficult. This is just a quadratic function. What we did in class, it was way more difficult. Okay, I'm hoping you're going to go back and review this. I'm hoping that you're moving forward. You're going to spend way more time on this class, please. I don't mind begging you. I tell my students that I perfected the art of begging. I don't mind begging my students, please. You can do this, please. Is there any question that you would like us to go back to? Anything that you'd like to see again before we move on to chapter 2? Anything?
I had one question, but it was just about the one that we just did, because I think on the test I differentiated it, or I did the c of x over x, and then I forgot to differentiate it, the second part. So when it like the format it was in, like on the test format, it was like c with a line over it. Does that mean c of x over x?
Yes.
Oh, and then differentiate. Okay, I think that's where I got confused.
Yes, so it says find the rate at which the average cost. It's a different notation. It's easier to write, to type. Yes, so I'm going to look at what you entered. And I give partial credit gladly. So, okay. Good, thank you for letting me know. Good, anything else? Other questions? You did very well, Haley, I can say that.
Thank you.
Yeah. I hope everyone will get caught up. Okay, is there anything else? Thank you for sharing all these experiences with me. This is very important to me. Is there anything else that you want to go back to or need me to explain? Okay, in that case, and you can always stop me. In that case, let's continue with chapter 2. Okay, a lot of algebra in chapter 2. We are going to look again at two functions, the exponential and the logarithmic functions. The reason why they go together is because they are inverses of each other. So if I apply a log to an exponential, I get plain x. No operations happen to x. If I apply the exponential to a log, the exponential will cancel the effect of log on x, and nothing will happen to x. Now, if you remember, the exponential function is a friendly function. So the general form is this. This is the exponential function. It's called exponential because the power, the exponent, is the variable. Exponential function. Not to be confused with, let's say, with x to the third. This is not the exponent. This is the base. But when the exponent is the variable, that's when we look at an exponential function. As an example, 3 to the x power, 1/2 to the x power, and two very important functions, 10 to the x and e to the x. These are all exponential functions. They have a number as the base, and the variable is the exponent. Now, when the base is larger than 1, the graph looks like this. When the base is smaller than 1, the graph looks like this. So this exponential function has two different options, like the quadratic function, opening up or opening down, upward, downward. The same thing here. So this is a to the x for a number greater than 1. This is a to the x as well, but for a small, between 0 and 1. So again, if the base is a number greater than 1, the function is increasing very fast. If you remember, the pandemic didn't happen a long time ago. They were talking about flattening the curve because it was going so fast and increasing in the number of people getting sick. They said, okay, let's try to flatten the curve so it does not increase so fast in the number of people getting sick. This is the fastest growing function, the exponential function with a base greater than 1. This one is decreasing on all its domain. And as you notice, no problems with the domain. The function exists everywhere. The function exists everywhere. No gaps, no asymptotes, nothing. Very good, very friendly function. Now, these are very special functions, and they are so special that they have their own key in the graphing calculator. So right here, do you see when you activate the second key, second, right here, see what happens? 10 to the x. So it's right here, it's activated with a second key. It can be blue or yellow, and here it is. Another key, I don't know where it came up with this because I didn't give any value for x. This is very weird. Okay, so with second and e, okay, e to whatever. Let's see what happens if I put x. That is really weird because I didn't give a power to x. I just said x. Let's see what happens now. Wonderful. Don't even look at this. This is ridiculous. Okay, so the base e. E is it's called the Euler number, a mathematician who showed how important this number is in real life situations. Okay, and this is called the common exponential function, and this is called the natural exponential function. So common exponential function, natural exponential function. Euler's number. It bears his name because he said, okay, like with the pi. What was that pi? Remember, how did they come up with pi, which is 3.14, la la la, and goes on forever? How did they come up with this? Well, they measured circumferences of circles. And when they divided the circumference by the diameter, they came up with this number all the time, all the time. So in this circle, they measured the circumference and they divided by the diameter. And at this circle, they measured the circumference and divided by its diameter. And then at this one, they measured the circumference and they divided by this diameter. All these, the circumference over 2 times the radius. For all of them was this number, always, always. They got that number. So the same thing here. Euler showed that this number is the best base of an exponential function for population growth, bacteria growth, fish, birds, and so on and so forth. He came up with this. This was the best base to approximate these functions of the population growth, bacteria growth, and so on and so forth. So in the same way, this was not 2, not 3, not 2.5. This exact number was the best option. And if you want to know what this number looks like, all you need to do is put the second key and the division key to power 1 and just press enter, and it's 2.71828 la la la. Okay, so this is called the natural because it comes frequently in the nature in real life applications, and this is common with the base 10. Okay, now let's also talk a little bit about the other function. Let me see the time here. Okay.